Welcome back, guys. In the last few classes we saw the working of a PN junction diode, and we also saw its working in forward biased and reverse biased condition. So today we'll finally see some fruit to our hard work. We will be seeing one of the applications of a PN junction diode. Okay, so it is used as a rectifier. So what is a rectifier? A rectifier is a device which converts alternating current to direct current. PN junction diode is used for converting alternating current to a direct current, and the process of converting AC to DC is called rectification. And we have two types of rectifiers: half wave rectifier and full wave rectifier. First of all, let's have a look at half wave rectifier. So this is the circuit for a half wave rectifier. We need an AC input, a transformer, a diode, and a resistor. The AC input cycle, which is to be rectified, is fed up to the primary coil of the transformer. So what is the function of a transformer here? It's simply to step up the voltage to our desired levels, and the secondary coil of the transformer is connected to a PN junction diode through a load resistance RL, and the rectified output DC signal is obtained across the load RL here. So this is our input, AC input, and during the first positive half of the AC input cycle, which is this cycle, during this first positive half of the AC input cycle, let us say this side is negative and this side is positive in the primary coil. Now due to Lenz's law, this side will become positive and this side will become negative, which means the diode is forward biased. So thus the diode conducts and current flows in the direction x to y through the load resistance RL. So during this first cycle we'll get output, okay, and during the negative half of the AC input cycle, the polarity changes. Let's say now this side becomes positive, this side becomes negative, and according to Lenz's law, this will become negative and this will become positive, which means that the diode is reverse biased, and we know that in reverse bias condition the diode will not conduct, and hence no current will flow through the load resistor RL. And so what happens? Will not have any output during this half, and again in the next cycle same thing, this will become positive, this side will become negative, and again diode is in forward biased condition and it will conduct, and this cycle goes on and on, okay, hence it is known as a half wave rectifier. And we can clearly see that the output is not strictly DC. We get what is known as a pulsating DC, and the average value of the output is given by V average is equals to V naught by pi, or you can write it as 0.318 times V naught, where V naught is the peak value of the input voltage, okay. This is input and this is output. So now we'll have a look at the simulation, okay. So this is our half wave rectifier circuit, and this is our input signal, and we are using a step off transformer, and you can see here our voltage is stepped up, and we'll now see our output across the load resistance RL. As you can see here, only during the positive half of the AC input cycle we are getting the output. Now we'll have a look at full wave rectifier. Why full wave rectifier? Because the output of a half wave rectifier was discontinuous and it was not efficient. Why not efficient? Because it was only converting one half of the AC input cycle, and the output was a pulsating DC and it contained AC components as well. Okay, so that's why we'll have a look at full wave rectifier. So this is the required circuit for a full wave rectifier. Here, instead of a normal transformer, we have a central tap transformer. Here the AC input is not shown. Let me just draw it here for your reference. Okay, so the AC input is fed to the primary coil of the transformer. The P side of both the PN junction diodes D1 and D2 are connected to the ends A and B respectively of the secondary coil of the transformer. The load resistant RL, across which output voltage is obtained, is joined between the common point of N terminals and central tapping of the transformer. So this is our AC input cycle. Okay, and again let us consider that during the first cycle, during the first positive cycle of the AC, this side becomes negative and this side becomes positive in the primary coil, and due to Lenz's law, again this side will become positive and this side will become negative, meaning that the diode D1 is forward biased and the diode D2 is reverse biased. So only diode D1 will conduct in this half. So the diode D1 will conduct and the current will flow to the load resistance RL in the direction X to Y, and we'll get the output here. And in the negative half of the AC input cycle, the polarity changes. And now the diode D2 is in forward biased condition and the diode D1 is reverse biased. So the diode D2 will conduct and again the current will flow through the load resistance RL in the direction X to Y. So again we'll get the output like this. And again in the next cycle diode D1 will conduct, and again in the next cycle diode D2 will conduct. So again this cycle goes on and on and on. Okay, and we'll get our output as this. And again the average value of the output is given by the formula V average is equals to 2 times V0 by pi. Why 2 times V0? Because in the half wave rectifier we were converting only the half cycle, but here in this case we are converting both the positive and negative cycles, so that's why we need to multiply it by 2. Okay, so again let us have a look at the simulation of the circuit. This is our input in the primary coil of the transformer, and again we are using a step off transformer. And we'll see that the AC voltage in the upper half of the transformer and the lower half of the transformer will be out of phase by 180 degree, as you can see here. Let us not see the waveform of the primary coil. So These are the waveforms in the upper half of the transformer and the lower half of the transformer. Why is there a phase difference of 180 degrees? It's because of the central tap. Okay. Now let us see the output. So you can see here the output. So that's it for today, guys. See you in the next lecture.